Cartesian coordinates. And then to be horrendously evil with you, I have pre-prepared all the notes for separation of variables in spherical coordinates, which is usually the stuff of nightmares. Okay? And I want you to revisit this nightmare with now more confidence in what actually the big game is. So we are now going to repeat absolutely exactly the same thing, but just in different circumstances. Separation of variables in spherical coordinates. So the first thing we're going to do is write the most horrendous equation from the very beginning, just to get it over and done. And what is this equation? It is the Laplacian in spherical coordinates. Spherical coordinates are theta, phi variables. A big mess when you take these second derivatives, lots of factors. You do not have to know this equation by heart. Remember, this is not the meaning of the green box. The meaning of the green box is if I put that in your face, you can use it. Okay? Namely, you understand every symbol in that, and you can operate any operator contained in that. Okay, so that's it. I mean, it's great if you remember it by heart, but yeah, I mean, I guess there are less useful skills in life, but you know, this is not going to make you famous. Okay, so in what circumstances do we want to do separation of variables in spherical coordinates? Well, once again, we are looking for symmetries. And the symmetry that is really useful here is so-called azimuthal symmetry. So this is a problem where if you can find an axis around which you can rotate the whole setup and leave the setup invariant, then this is great. This is azimuthal symmetry. If you can find a whole rotational symmetry, complete rotational symmetry, then this is great, because this is like, you know, two independent azimuthal symmetries in there. And then it's even simpler. Azimuthal symmetry is really, you know, think about the kind of donut-shaped potential or configuration. You've got one rotational degree of freedom that leaves it invariant. Okay, so that's the idea. So here, just like we did in Cartesian coordinates, we went from 3D to 2D. Here, we've got no dependence on this angle phi, this azimuthal phi. So this goes, this whole term goes, and we're left with two different parts. One part which depends on the radial coordinate, one part which depends on the polar angle. Okay, and again here we follow exactly the same, you know, random path. We say, fine, that's my Laplace equation. I've got r dependence here. I've got angular dependence here. Let's assume that my solution is just a factorized product of two different functions. One a function of the radial coordinate, one a function of the polar angle. Absolutely exactly the same templated reasoning that we have here. We write the two things, we divide by the thing. We've got a thing that depends only on r, thing that depends only on theta, and then we are looking for orthogonal functions. You know, we're looking for a complete set of functions that solve these things. Now here, the radial part is extremely simple because it is solved by power laws. So just simple powers of the radius are going to solve. And there are two independent solutions because it's a second order differential equation, r to the power L or 1 over r to the power L plus 1. And this is the case for a given constant. Just again, similarly to the Kn that we have here, here we just choose an L, which can be an integer. Okay, so for the radial part, it's easy. For the angular equation, it's a little bit more sporty because here, you might have met those in quantum mechanics, not yet, I'm not sure, Legendre polynomials. Okay, are you familiar with the Legendre polynomials? You've seen them, right? Okay, so once again, the vision of the Legendre polynomials, what's the idea? The idea of the Legendre polynomials is that they are orthogonal polynomials in the interval 0 to pi, weighed by the measure sine theta. Okay, that's what they are. Said otherwise, you can rewrite by a change of variables, they are orthogonal polynomials in the interval -1 to 1 with the weighing function 1. the simplest orthogonal polynomials you can have. Then you have some conventions for those. I give you all the conventions. The conventions are that the seed polynomial is just the constant 1. Second convention is that all Legendre polynomials, when evaluated at the point 1, take the value 1. And with these two things, you can derive the whole series of polynomials. First of all, this has as a consequence that you can write the orthogonality relation between Legendre polynomials in this form here. It's got this annoying constant in there, but it's just a question of tabulating it. And then you can write the general solution as a combination of products of these radial plus Legendre angular solutions. And really, morally, it's absolutely exactly the same thing. I'm just giving you some complete relations for these for reference. They're all in the notes here. The conclusion is that the solution of the Laplace equation for azimuthal symmetry can always be written in this form. And then it becomes a question of just fitting your coefficients. So the idea here is that there's a long story to get here, which you do carefully once in your life at least, unless you're teaching it. In this case, you do it every year. Okay? You do it once in your life, and then in your bathroom, you know, above your mirror or maybe on your toilet door or something like that, you write that. Phi of r theta is equal to summation L is equal to 0 to infinity of AL r to the L plus BL divided by r to the L plus 1 times PL plus theta. That's what it is. It's always like that. Okay? You don't have to know it by heart. But you should be able to use this when you have a problem with azimuthal symmetry, and I'm asking you the solution to Laplace's equation. You say the solution to Laplace's equation is summation L is equal to 0 to infinity, blah, 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 blah. And then you look at your boundary conditions, and with your boundary conditions, you tell me what A0, A1, A2, A3 is. You tell me what B0, B1, B2, B3 is. And that's your solution. Okay? Absolutely the same mechanics. There is nothing new under the sun here, except for different functions, different orthogonal functions, more complicated orthogonality relations. But again, morally, exactly the same thing. Question?
This was the case with spherical symmetry.
Azimuthal symmetry. So not full spherical rotation symmetry, just around an axis.
That's around an axis. Okay.
Yeah.
It's an ending from Mars, but then we got.
Yeah, exactly. Yeah. Okay, so I will leave you with this. Actually, there's an example worked out here that you can look at. Again, here I kind of give you some boundary conditions, and you just fit. And again, to fit the coefficients, you again have to invoke the orthogonality of these basis functions, but it's exactly the same story. We'll see you